Okay, good evening. The stream is now live and the chat should be open here. Today's topic is Tesla Coil design, a little bit of theory, mostly in the practical sense, and then a whole lot about the compromises that has to be done. Okay, I just have to turn some sound off there. And a whole lot about the compromises that has to be done while designing something like this. First I have here in the background is my DRSSTC design guide. It will not all be about this, but as I wrote this and this is based on my experience, this is also the kind of basis for the talk tonight. But at first, tonight's drink, it's a local brew. It's called the Albani Odense Classic. So much talking gets you thirsty. And I can see that all the people in the chat says hello, and thank you very much for spending some time with me tonight, and cheers. Always good with some local brewed beer. Alright, so the plan for tonight is to give you a little insight into how would you go about to start building a DRSSTC. As I at some point made this graphic that you see here on my side that just says push button, receive lightning, because it's kind of a way how simple it is, and then again, not at all. There is a 15 topics in the guide so far. I will not go in detail with all of them. A lot of this requires some self-study. Requires a lot of reading and looking at others' projects to build your own. But let's first jump to the FAQ that I wrote for this, because building a Tesla coil comes down to three things really. You have how much money do you have? That's kind of the highest governing criteria. Second is coming along with the third, which is thermal management. How high a temperature rise would you allow in your design? Because that decides the third, the lifetime of your system. Is this something that you think will just be used for a weekend, show your family, or is it going into a museum to be used every day for showcasing lightning? These are pretty important factors in deciding how much money and time you put into your design, but certainly also how you handle the thermal rise issues. A few other issues is something like handleability. How well can you manage to move or set up a coil system alone? Because building huge Tesla coils is cool, but it's also becoming a 2 or 3 man job suddenly to just move it and set it up. I tried to illustrate this with this little graphic. This is me, I'm 1.8 meters tall. The blue coil is the first coil I built. That's a fairly manageable size, and there's absolutely no problem in either storing it or moving it around alone. Now the second one I built, the green, that's a small tabletop. You can put that in a cupboard if you don't want to look at it, and it's no problem at all. But if you want the 4 meter lightning generating machines, as the red one, the DRSSTC3, you suddenly face some whole other problems. The individual parts become incredibly heavy, and the complete coil assembly weighs around 120 kilograms. And that is a major problem, because I am just on the verge of not being able to set up this coil alone when the secondary coil weighs around 40 kilograms itself. So, moving on to the, okay, this is probably too small for you to read, but it's a complete part list for the 3 different coils. And what I paid for them. So if you scroll down to the bottom where the summary is, the total cost for my smallest DRSSTC, the green one, was around €100, while the blue one was around €400, and the large one was €1,400. So the price kind of quadruples with the size, and so does the complexity of the build, and so does the weight, and so does the problems with storing it later on and just keeping your parts safe while you build something that is much more expensive. You also have to take into account that it's much more difficult to take care of in storing and so on. So you really risk damaging some expensive parts. And hello to the newcomers into the chat. Remember, you can just ask any questions in the chat, and I will try to keep an eye on it on my laptop and answer to my best knowledge. So, how do we go about building a Tesla coil? Well, first there is reading to do. You should study the theory behind the operation, but it's not crucial. It's mostly if you have a deeper interest in how the inverter works and how you impedance match between the primary circuit and secondary circuit. For this, there are a really good old website, which is Richie Bernard's Tesla Coil webpage. As you can see, he designed this in the 90s, early 2000s, and I think the latest update is, if you go to the update list, you can see 2008 was the latest update, so it's 10 years old. But it has one of the most comprehensive theory chapters on solid-state Tesla coils and how inverter works and so on. This is something you should look into, but it can be hard to relate the theory when you have not yet built a coil. Because you are not aware of the problems that lies behind the explanations and so on, and why these design choices have been made. So what I really encourage people to do is to look up other people's work and replicate it one-to-one. Now there is Steve Watt's original HTML site here. He has a whole chapter on the solid-state Tesla coils, and here his DRSSTC2 and his new DRSSTC drivers are really the chapters to read. But his older designs has a lot of pointers into how his newer driver works, so you really have to read all the pages here in order to understand how he developed his driver, which is the most used driver today, or at least they are based on his design, where there is the new DRSSTC driver, which is known as the 1.3, and there is the newer one with phase lead based on Finn Hammer's predicted design, which is the 2.1B. I will again put all links to the sites that I show tonight in the description of the stream once this is done. Another really good site is Lone Ocean's Tesla coil build logs, because he writes very well documented build logs, and he has a lot of details on them. While Steve Ward's website has all the vital details, you will need to piece a lot of it together from his other pages and so on, and also the related forum threads that were on 4hv.org at the same time. But all in all, if you know what you're doing, you can use Steve Ward's website as a good starting reference. Now, Lone Ocean's website is very thoroughly made with all kinds of really awesome pictures, and he gets down through the theory of switching and so on, and explains a whole lot of how it works along with building it. So that's a really great website. Then there is my own. I would say that I do not go in such a great detail as Lone Ocean's, but I do put a lot of effort into documenting all the different steps that I have been through, and a lot of technical details. There should not be left any technical details that you should be in doubt about. And also I try to include all my failures, because others are likely to encounter the exact same failures as I did. Yeah, this is mostly a complete log of how I go from idea to sparks. So find a coil that you think you can manage to afford, and have enough tools and experience to build or learn how to do it, and then try to replicate it to your best knowledge. And ask for help on forums. Do not be afraid to look stupid, or so to say, because there is no such thing. We all started asking questions that I would today consider maybe a little too obvious to answer, or that I could have read somewhere, but you can't know where to find all information. So in order to start, there is really, when you would say, there are multiple entry points into it. Either you have found some good capacitors for a MMC, or you have found some cheap IGBT bricks, or you have a certain secondary sewer pipe in your holding, or you can get it from some home improvement center or something like that. And these are at most the entry points that people get some part very cheap, and then decide to design the rest of the coil around this. Now the dangerous approach here is, of course, that you might have gotten one part cheap, but the rest of the maybe 10 vital parts can be very expensive. And also, cheers. So I really like to take my design start in the IGBTs, and then go on and look at the MMC, as these two quickly become the very expensive part. Now secondary coil is of course no exception, except that as long as you keep your secondary coil smaller than a 160 millimeter diameter tube, it is not getting too expensive, neither in the tube or the copper and varnish that you need. But once you get over this point, it simply becomes so heavy, thicker wire, you need more varnish, that the cost to the secondary coil and top load increases very fast. So moving straight into the DRSSTC design guide, I tried to write this from a point where there's not really a red line. You can pick out the chapters that you want to look at, and that you need right now, where the IGBT chapter concentrates a lot about the thermal management that is needed. The first few chapters are about how you understand the key datasheet specifications that are vital to us when we want to abuse a IGBT, because that is really what we do. We take something and drive it at a higher peak current that it's designed for, as I explained in this chapter, that when you do resonance switching, you have a lot of advantages when it comes to losses and turn on and turn off speeds, as the resonant current helps driving the IGBT on and off, and it doesn't have to be done completely with the through the gate drive. Now, a lot of people worry about the higher gate drive that we use in IGBTs, but as IGBT gate to emitter voltage is all relative to the amount of current that the IGBT will be able to conduct, it is actually not a problem with punching through your gate before you hit over 80 volt DC. But then you would have long killed the IGBT from overcurrent anyway. So that is really not a huge factor. Another interesting point is the collector emitter saturation voltage, as this is the absolute key factor in our conduction losses in the IGBT. The higher this voltage is, the higher our losses is. Collector emitter voltage, it's not really a big issue, as most people, even with a voltage doubler, we use 1200 volt IGBT bricks, so this is hardly any problem. And even switching spikes have very low energy, so simple Snubbers circuits can take care of these. Now we get to the point here about switching times. And switching times is always a good issue that people ask about. How fast can I drive this IGBT brick? And you can drive almost any IGBT as fast as you want, but it's not really sure that you will can do it for a very long time, because it will heat up fantastically fast if you do not let it, or let it have time to cool off. If we go down here. Oh, hello, nice lady. Here I try to illustrate the... go away. Now, if I try to illustrate here the linear region, and this is all about how long time do we spend on turning on the IGBT, because this is where we have the turning on losses and the turn off losses. These are the highest losses that we have, and if we do not have zero current switching, but are hitting a little to the side, which we will, because we cannot control it that precisely, we have higher losses as we have a current as we switch on and off the IGBT. So when we get down to our thermal impedance, now we're getting to the points where it's more about how fast can we drive these IGBTs. Now the good thing about a dual resonant solid state Tesla coil is, of course, that I'm sorry, I forgot, I had scrolled a bit away from the chat, so I will read the two comments in a second, and I will answer the questions. Thermal impedance in IGBT bricks is all about a duty cycle. And the duty cycle in a DRSSTC is very, very low, as we are running around 200 to 300 microsecond on time. So even here we get placed at the graph very high up, as you can see here, that the single pulse graph is way down the chart on the Kelvin per watt, or Kelvin rise per watt dissipated. So this is a great help already there. Then we count with a factor of 4 less for a resonant switching inverter, or is it 10 times lower? But that doesn't. It depends a bit on your BPS and on time, and so how much your duty cycle really is. Okay, let's see. Experimenter 99 asks me, he's planning to switch 2 half-bridge bricks in parallel to increase the current handling of the H-bit, so there will be a total amount of 4 bricks in the assembly. It worked perfectly, but I want more primary current. Do you have any advice for me to ensure that the bricks share the current equally? It's all about bus inductance. Here it is important that you design a really low inductance bus, that you have your DC bus plates all parallel to each other, one big plate even covering the terminals. You must ensure that your current sharing from the DC link capacitors is shared evenly, that you have the same length wires from your rectifier bridge to the IGBT bricks. You must be sure that you do not supply your bridge at one end, so you have a higher peak current at the top IGBTs, but you must supply it crossing everywhere to ensure that you have even current path everywhere that it is possible. Another way you can do this is of course also using chokes or common chokes, that you have a kind of isolation transformer that you feed the two inverter outputs through to a common output, but that will get very costly in huge variety cores or toroids. Another thing is ensure that you have even cooling, so you do not have one set of IGBTs that will maybe go into thermal runaway. But overall, people have pretty good experiences with paralleling IGBT bricks without doing too many jumps to get this working. But never assume that you have the doubled current handling if you have twice the IGBTs. It is more along the lines of that you can push it maybe 20 to 40% higher, but never above 50%. When you do parallel diodes, it was never recommended to go higher than 30% above, because when you have no control of your real bus inductance, you have no control of where your current goes. So never assume that you can conduct twice as much current with twice as many IGBTs. I hope that answered the question. Now, when dealing with the switching speeds in IGBTs, there are two terms, which is Fmax1 and Fmax2. Fmax1 is purely looking at the datasheet rise and fall times. So it's simply the combined times for switching on and switching off. These will often give a misleading value. Here it is calculated in regard to 10% duty cycle, which is very pessimistic in a DRSSTC. But nonetheless, this is the example that I used. Now, here I can see that my example of I think this is a CM300. Oh, it's a CM600. That I can switch this at 230 kilohertz. Now this is of course way too high, because there's no way I can build a driver. There's no problem in building a driver that could drive the gate charge at this speed, but the conduction losses in the IGBT itself becomes our new problem, and this is where Fmax2 calculations come in, because here we do not really look at the switching times as per se, but we look more at the switching losses in energy amount. And take that into account with a design specification to our temperature rise. And as I mentioned at the start of this stream, that it all comes down to money, temperature rise, and how long do you want it to live. Because the longer you want it to live, the less temperature rise is to be allowed. I calculate with a 30-degree temperature rise, and this is for a single pulse, that the die inside the IGBT is allowed to rise from, let's say, 50 degrees Celsius to 80 degrees Celsius. Then we have to give it enough time or conduct a small amount of power that it can cool off back to 50 degrees before we try to switch a large current once again. Because if we do not have if we have a too high temperature rise, the IGBT with its thermal impedance cannot cool down between the individual pulses. So we will get a quickly rising temperature. Then it's suddenly 55, 60, 70, 80, 90, 100. And above 125 degrees, we are running out of headroom in the datasheet. So once we come above this and we keep switching, goodbye silicon. You will either melt it or you will have it explode from thermal runaway and simply conducting too much current. So what we have to do is we have to imagine some numbers, because datasheets do not specify extreme numbers like we want to. There is no specifications of 2000 ampere switching in the CM600 datasheet. There is only for 600 ampere, or I think it's up to 1000, maybe it's 1200. Yeah, it's specified up to 1200 amps. So what you can simply do is you extrapolate your graphs, like I did here. It's made in Paint, so it's a rather good job, if I should say that. And you can simply extrapolate the saturation voltage to know more about the conduction losses. And this goes with a lot of Tesla coil design. We have to guess a lot, we have to make up numbers, we have to assume a lot of numbers, but in the end it will work. It's all based on experiences, and anything designed in Tesla coils is plus minus 3 dB, so it's give and take. You decide. We are playing here. We are taking it to the maximum and seeing how far we can push it, but here I also try to, let's try to push it within some reasonable limits that can make it live for at least a little bit longer. So first, I can calculate my conduction losses, and with the thermal impedance of the IGBT and our allowed temperature raise, we get a total power that we can dissipate in that time that we have available. So we can actually dissipate 370 watts of losses in this CM600 IGBT between pulses. But to find out how much is we really switching, because switching losses in datasheets are once again only given for hard switching. Now hard switching is when you turn on and off your IGBT with default current across it. When we do resonance switching or soft switching, we switch at zero current, so this should not be the case. But as we cannot really control how much or how close to the zero current switching that we get, we have to assume that we will be hitting a little bit to the sides of the zero current point, and this is where we can estimate that we take the hard switching losses and we simply assume that the switching times are faster, because they are faster in resonance switching, and we can devalue or what do you call it? We can calculate down the hard switching losses into some assumed soft switching losses. Now this we can then again read out on a switching loss energy table that we can be lucky to find in the datasheets, or else we will have to find a datasheet for another similar IGBT and simply assume that it is in the same league as that. And once we get down through all this, we correct the result according to our drive voltage. As I mentioned earlier, that the harder we drive an IGBT, the more current it can switch, and the less losses we have. And we can simply see that when I will accept a 30 degree temperature rise, I can switch a CM600 IGBT at 2 kiloamps at a maximum of 56 kilohertz. Now my large coil is resonating at 37 kilohertz, so that is absolutely no problem. I'm staying beyond or below the thermal limit of this IGBT brick. And this is really the most vital part of designing a Tesla coil, in my opinion. Because now we have designed a safe operating topology or method for our IGBT bricks where we ensure that these will live. And from here we know that we have a peak current of 2 kiloamps, and we can take this on into the MMC designer. Now, I have not finished the chapter on the MMC design, but we can take a sneak peek here on the draft that I'm currently writing on. Again, I talk a little about what is the expected life span of the Tesla coil. Then how about we choose the value of the MMC capacitance. Now this all comes down to a lot of about impedance and impedance matching. That what kind of drive method do you want to use in your Tesla coil? And there are like two. I can say there is you can have low impedance coils which operate at very high peak currents, but with very low on times. These have the least conduction losses, but they are also the most expensive to build because high peak currents is just simply asking for building something that is very expensive, because you have to build something that can really stand up to the task. Now, if you build higher impedance coils, you can also get the same spark results, but you do it with a lower primary peak current, so you can build it cheaper, but you are forced to use longer on times, so the conduction losses suddenly start to govern the problems to be solved instead. So here a lot of cooling and thermal management and inductance matching and so on becomes the really big issue. Okay, let's see, Experimenter has he asked me, I have a chart of IGBT bricks, and he has SKM 200 bricks at 75 kilohertz. He pushed them to 1100 amps. Yeah, and I really agree that if we're going back to the IGBT selection here's the chart that he talks about, that a lot of these IGBTs should be seen as proven designs that can run for a long time. There are not mentioned any experimental switching speeds or currents here that should not be long-lived. This is all based on a fairly good life cycle time. Because I would assume that you can push almost any IGBT to the double, but the wear and tear on the IGBT die itself and the bonding wires inside the IGBT gets very high when we get into the extremities of current switching. So again, this comes down to how long do we want this to live. I have seen a lot of IGBTs inside where the silicone gel is cooked or charred, or you can really see that it has taken some damage due to heat. And if you want to research this topic further, you should look into micro cracks in IGBT bricks due to temperature rise and fall. This is a really interesting topic where through microscopy that it's investigated how the silicon die simply starts cracking underneath and loses connection with the copper heatsink, and then it will of course suddenly explode due to thermal runaway, as it simply can't get off with its heat, and that is a typical heat damage. So what I try to do in the MMC part here is simply put up a capacitance range within where the secondary or primary impedance will match the secondary impedance tables that are in the secondary coil design chapters. Other than that, I talk a lot about voltage rating and RMS current rating in this chapter. As you can see, it's not completely done yet and has a lot of notes and so on. So I hopefully get time to finish this chapter later on. Now these covers the two most important chapters, the IGBT and the MMC. Now, when we come to a secondary coil design, what I recommend here is I set up a lot of tables, and I talk a lot about spark loading and spark loading doing ground strikes, and it's a lot of difficult subjects to understand, and how impedance and Q factor and so on, how this affects the system. But it all comes down to that we have to think of the arc as or the spark as a huge resistor. It's something that we put a lot of energy into. This is our end product. We are feeding a huge spark with energy, and we have to look at how this spark loads down the system, because it will load down the secondary. The secondary will change its resonant frequency as the spark represents a capacitance, not just a resistive load. So it's a really complex matter of plasma physics, almost also weather physics. How is your pressure, temperature, humidity? A lot of about electricity. How is current moving? How is air displaced in ionizing clouds, and so on. So okay, not ionizing, that would be bad, but how ions and electrons penetrate and divide through an insulating matter like air is. So it's so complex that there is really a very few people that could explain this, and I certainly cannot. I do not understand the complete thing that is going on, except I know that I can create huge sparks, and but that doesn't mean that I have to understand the exact physical properties of the spark. So the secondary chapter is mostly about impedance matching, and how you again calculate losses and so on. Here I also try to describe in tables how some good matched what do you call that, height diameter ratios are, some good impedances, what kind of wire diameter you should use, and then the expected resonant frequency. So this makes it pretty easy to match over to the IGBT chapter, that at a certain size coil you could choose to build a certain size secondary. But now remember, these are all best practice choices. These are all, when you say, you can build something here that works, and it works very well, but it's not going to be cutting edge unless you really optimize on each parameter. But then again, you really need to build some coils, gain some experience before you can do that. So these are all very good starting points. Then I added some more about how to choose wires, secondary foil or secondary coil form and material, and so on. So these are also how to wind it, and so on. These are all something you should read. It's not something I will go into details with right now. A lot about varnishing, terminations, how to avoid these kind of failures that some good users have sent me some pictures in from. So what kind of tools should you use when you then want to design this? Now I showed you my IGBT chapter. This is how you should calculate that. There is currently no online calculator or any spreadsheets for that. That's all done by hand, and it's really not that complex. So, but if we take a look at the MMC calculator, okay, and see Malte asked how important is varnish for very small coils, around 20 centimeter tall. Well, you can easily find people who have run coils which is just wrapped in food foil, some clear plastic, just to keep the windings in place. Because the insulation thickness on the copper wire itself should be good for at least 600 volts in the layer. So if you have two layers against each other, you have 1200 volts per turn in insulation. So if you're using a relatively thin wire, you would have some 100 kilovolts of insulation resistance at 20 centimeters coil. So the varnishing of the coil is not really to prevent arc overs, is as much as to keep the windings in place, because different temperatures will expand both the form and the copper wire. So you can suddenly have loose windings that will overlap, and as soon as you get something that is not even on the surface of the secondary coil, that becomes a problem. You will suddenly have a small corona discharge, and suddenly that will attract a spark, and you will burn a hole in your insulation, and it's done. Then you will have to make a new one. So the more varnish you have on it, the higher insulation strength is also the whole secondary as a complete component, but it will also survive strikes directly to the secondary or raising sparks, which is often a product of too high coupling, where you can see sparks going up and down the secondary. So you can avoid a lot of destroyed secondaries by giving it just 1 or 2 layers of varnish. Okay, the Falk asks, do you know of anyone using SMD MLCCs for the MMC? Is it feasible? Now I have not looked too much into doing something with SMD capacitors, but I do know that the MLCC capacitors are very susceptible to temperature damages. That again, micro-cracking inside the capacitor is often a failure mode seen in electronics today. So that could easily become a problem if it's not really controlled, that your current paths and the inductance of such an MMC. Because the good thing with the actual capacitors or snubber capacitors is that you dissipate up to 2/3 of the heat inside of it through the terminals. And often you can mount these on some larger copper rails or something like that. But I think the small size of the SMD capacitors itself is a bad starting point for the whole thermal management perspective. So I would certainly stick with larger through-hole component MKP capacitors, simply because they can be soldered to some bus bar or something to take off the heat. But I would really recommend that you try it and write about it on forums, so other people can learn from your experiences. It's an interesting point, because if you made a smaller Tesla coil, of course you can use it. A lot of these thermal issues is first an issue when we get above a certain limit of primary peak current. So are you operating at some sub 500 ampere? That's, well, yeah, don't we just call that leak current? Or yeah, fault currents. Everything below 500 ampere is fault currents. But I made this MMC calculator in order to make different designs easier. Now you can load a example coil here, one of my 3 coils that I built, and it will plug in the primary peak current and primary inductance and frequency and so on. And there is a list of different capacitors that is proven in the community. So if we take the large DTO snubber capacitors that I use in mine, it is simply a matter of clicking up and down on these buttons. We can see the voltage rating, the MMC capacitance, and so on. And where it really gets interesting is up here is really for a pretty fast design. But when we get down to the advanced results, this is where we get the primary impedance and the matching impedance and reactances of these single capacitors. And the temperature rise. Again, this, as with the IGBT bricks, it all comes down to how high a temperature rise do we allow. And there's just a small paragraph out here on the side that how many degrees Celsius is acceptable. And it's here's a comparison between what are the actual values of the design of the coil that we put in, and then what is the rating of the MMC that we have put numbers into. So it's simply a matter of that the MMC rating has to be higher than the actual values. Okay, now Ephard asks, as the large filtering capacitor on the rectified mains, a single or more in parallel can supply more current. And of course, the more the capacitors you have in parallel, the higher current capability do you have. But you do not exactly have much more current available, as it comes down to the ESR of your DC link capacitors. So if you're using regular electrolytic capacitors, we can see this in the DC bus capacitor chapter. Here I talk first about some voltage sharing between capacitors in parallel and series. Something about how you should ensure yourself against automatic discharge, and then current sharing. Now this is something that I mentioned earlier about the whole inductance and current path matching methods. That, as we can see here, if we place things in parallel, it is important to ensure that it has even current sharing. Because in the bottom illustration here, C1 would conduct maybe 50% more current than C4. So there's no doubt that C1 will fail here before C4 does. So here you have no benefit of the paralleled connected capacitors. But if you ensure a even current path, you have. So back to the question. Will more capacitors ensure more current? No, it will not. It will ensure that your capacitors do not heat up as fast. And I can also see that Ilya's pops a beer, so cheers Ilya. I'm also getting a little thirsty. The more capacitors you have, the more filtering capacitance is available. So this means that your ripple current and also the voltage ripple between bursts of current delivered to the inverter will be lower, because you have so much more capacitance available. In order to get more current delivered faster from your DC link to the inverter, you will have to use capacitors with a lower internal resistance. So this is fortunately for us, we live in a time now where DC link capacitors are changing from electrolytic capacitors to MKP capacitors, or polypropylene capacitors, the same type that we use as Snubbers, as MMC capacitors and so on. These have extremely low ESR compared to the electrolytic capacitors, so they will be able to deliver current in maybe a tenth of the time that you have from the electrolytic capacitors. So this gives a much more aggressive current delivery ability to the inverter, and it's also I know from Gizmo, which also built the large Tesla coils, that he mentioned that you don't even need as much DC link capacitance when you are using MKP capacitors, simply because they can deliver so much higher peak currents. Okay, so Paulux, he asks how to calculate the DRSSTC primary current. This I would write about in the MMC chapter. which is unfortunately not completely done yet. There, as you can see here, it really comes down to your primary circuit, and then how many. You say you have your primary inductance, you have your peak or your voltage that you drive the primary circuit with, and then you simply have to calculate your burst length, and then you see that for each cycle that you keep switching power into the circuit, the current will ring up. So this is actually how you calculate your primary peak current. I don't really recall that I have calculated this beforehand, because you can say that the primary peak current is maybe not that interesting in the way that I design a coil, as I first look at how much can I switch with my IGBTs, and then I build the MMC bank and the rest of the things to actually deliver that kind of current and be able to ring up to that kind of current. And you can say that since it's all based on how many cycles you conduct, that you can just switch for that longer amount of time until you hit your primary peak current. So this really only gets interesting when you're doing low impedance coil, where you want to look into how fast can you achieve your peak current. My approaches are at most that I just look at, okay, if I have to switch for 250 milliseconds or microseconds, well, I do that. Whereas some people maybe look into, okay, I want to switch below 100 microseconds and then achieve the same current. So it really all comes down to the impedance of the inverter, and then how long you want to have it turned on for. So that's another point here, that you can see a lot of these results of calculations are entwined between that. You need some numbers from the MMC calculations to do the IGBT calculations, but you also need to know your primary circuit impedance in order to make a matching inverter and so on. So there is really not that good entry point, as I mentioned earlier. You can have multiply entry points into start building your Tesla coil. And that is also the point of my guide, that you can pick out a chapter and you can go from there, and then you have to make up a few numbers and so on, but that's how we design it. There is really no one way to do things. So I hope that answered your question, and I hope I can find time to finish these chapters in a near foreseeable future. So I don't hope I lost too much track here. I was talking about the DC bus capacitance from another question. And again, here it's a little bit more how much DC link bus capacitance is needed. Here we simply look at the amount of energy that we pull out of the system for each pulse, how much energy is left. Then we can calculate the voltage drop of the DC link, and then just assume or say, do we think this is suitable for our coil? Okay, if it's not, add some more capacitance. Okay, getting a little dry throated here, so cheers. Okay, station 245 says that and what components you have access to varies. Could you please clarify it a bit more if that was a question? Okay, so I mentioned earlier that when I first started building Tesla coils, there is a few good resources that I used. Besides Steve Ward's website, it was pretty much down to Rich's website, and then for online calculators, I really love the Deep Fried Neon's website, because this is probably the only website that had some online calculators at this time, where the helical coil, the flat spiral coil, and the top load calculators are three very nice calculators, because they are dead simple. They can be used in millimeters, and here you can get some good estimates on your length of your coil and so on for the secondary coil, or if you're doing a helical primary coil. Then there's the flat spiral coil again. It's good for just a quick estimate on how much wire is needed, or if you have 10 meters of coil, how big a primary can you build, and so on. And then the top load calculator, because as you can see, this equation is rather stupid, as these are based on some research, practical, experimental numbers from some old papers. But again, very good for quick designing and quick checking out some numbers. Because when it comes to really designing something, there is nothing that beat Bart Anderson's Java TC. He also has a Java MMC calculator, but this MMC calculator is mostly based on spark gap Tesla coils, and is why I made my own, which is focused much more on the solid state. But if we take a look at Java TC, it can be a little bit hard to grasp all the input fields when you first take a look at this and know what to do with this. I have seen many people, when you tell them please go to Java TC and plug in your numbers and then come back. If we load an example coil here, we can see that we don't really need to put that many numbers in. There's a primary capacitor size. Then we have to specify some physical spaces around the coil, as this will affect the secondary coil resonance. Now, speccing out the secondary coil, we can use the numbers that we had from the earlier Deep Fried Neon calculators. And it's just radius, and then height from the to the bottom, and then height to the top of the coil, because the calculator of course assumes that you have a box underneath and some primary coil and so on, so the secondary coil is not sitting on the ground. You have the number of turns and the wire diameter, which you can just switch to instead of AVG. If you're using the American wire gauge, you can also do that. Now, primary coil, again, you can take your numbers from the helical coil calculator or the spiral coil calculator, and you can put this in. Now, here it's a little bit important to add the total lead length, as this is your leads from your inverter to the primary coil. So this also adds a little bit of inductance. So you can miscalculate your primary frequency if you do not add in all your inductances. Now, top load, here is a 4 different choices: toroid, sphere, disc, and cylinder. And 99% of people use a toroid top load, as it is the superior choice in terms of field shaping and so on. So here you simply add your diameters and you plug it in, you add it to the list. So now we can go down here and we have the results once we press run Java TC. So here we have a small presentation of the coil, and you have all the calculated inductances and capacitances that would be needed if you wanted to do any more theoretical modeling of Tesla coils, like if you like to calculate and simulate on spark loading and so on, that many people have experimented with models for this. But this is simply the most complete calculator there is around. You will find no other calculator where the whole calculation of all the secondary capacitances and inductances at the right frequency and loading and so on is really this complete. It's a really great tool, and when you come to the time where you want to adjust coupling and also tune your Tesla coil, this is the absolute go-to tool. You can see here that we also always have a recommended coupling, and here's the actual coupling. Well, now let's say that we would like to auto-tune it to a higher coupling. We can put in maybe 1.15. Then we can just run it again. Okay, it says that we go through, okay, what did it say? 0.15. Through a vertical adjustment, can adjust further. Okay, so there's of course some things that is not physically possible, like letting coils go through planes and so on. So you have to adjust some numbers in order for this to actually work out. But you can auto tune the whole coil to suit into what you really want. And this is a really powerful tool for this. There is no other tools that will do this for you. And what it does, it's simply adjust the primary coil and secondary coil heights in respect to each other. So you will have to go back up here and read out the new corrected numbers to your new coupling ratio. Okay, experimenter has a question here. He says, I measured the resonance frequency of my secondary plus top load, and it is around 75 kHz with simulated spark loading. Should I tune my primary circuit to exactly 75 kHz or lower for perfect tuning? I have done a few experiments myself with the simulated spark loading simply by putting on small pieces of wire out from my top load. That will have the almost exact impedance and capacitance resistance as a spark, and I still find that the result is misleading. But if your unloaded resonance is around 10% higher, then I would go for it, because when you detune your primary around 10%, you are around 5 to 10%. You are around the maximum output power detuning. So that is a pretty good rule of thumb to go for. But again, tuning is a very fine picking art, as this all changes with how the weather is that day and what is near the coil and so on. There's so many factors that really affects the resonance of the secondary coil. So it's really hard to give. You can say what you fine tune one day in your workshop will probably not work at all when you set it up out in an open field on a day with a whole other temperature and humidity and so on. So it's really hard to give out really good instructions on what is a perfect tune point. But what I do is I keep a log on how I tune it well in what environment. So keep a log on how close are you to the ceiling, to walls, to objects, are you out in the open, temperature, so on. That way you don't have to experiment every time you set up your coil, but you can look into your notes and see, okay, at these settings, these tuning points are the best results. So that's what I really would advise you to do. But the JVTC, absolutely a wonderful tool. You can even download it, you can use it offline. So really powerful tool. When it comes to driving your bridge, there is no beating the 1.3 driver from Steve Ward. This is his original design of the universal driver. And I would recommend using this for anything when you're not talking IGBT bricks. as long as we are talking small, fast IGBTs, there's really not that huge need for phase lead. But if you are using large IGBT bricks, there's of course use for phase lead, as this will lessen your switching losses. And I do of course not have a link for that right here. I will put it in the description of the stream. As many other things, this is very well hidden on Steve Ward's side, and it's not everything that is publicly accessible unless you know where to look for it. So another good site that I would like to promote is the data stream. When you search for gate drive transformer design, you are most likely able to find this site from Google. Has a very thorough description on the theory and practical GDT design, and a little bit on driver circuits. So this is really a good source to go to when you want to see some bits about what kind of wire to use, the winding techniques, and what kind of parts you can use, because often people ask, can I use this and this ferrite material? And a really good mistake that many people do is that they find some ferrite cores in ATX power supplies, but they are absolutely not suitable for gate driving transformers. These are only meant for jokes or for noise suppressing. So please never try to use any yellow cores from power supplies. Okay, Malda asks, have you ever seen a coil with a double toroid where the upper toroid can be lifted using pneumatics to change the secondary frequency? I've seen one. I'm curious how common that is. Okay, let me just grab a sip of beer. I have not seen that, and I would very much like that you post a link for that in the comment on the stream if you have a link for it. I know that Finn Hammer and Daniel Urenholt, which are two Danish coilers, they built some large DRSSTCs with automatically tuning of the primary. So you could experiment with the primary tuning on the fly. I don't know if they got to a point where it would be automatically tuning itself, but they certainly could experiment with the tuning during it running. I'm not sure if I see the advantage of changing the secondary frequency while running. Was it supposed to be to counter the frequency change because of arc loading? Because then even there it is getting way too complex to control, because changing two toroids apart from each other and changing the capacitance here, it will never be able to react fast enough and to regulate the capacitance fast enough to make up for the changes in arc loading. So, but yeah, it's an interesting approach, but I really don't believe that you could regulate your way out of arc loading problems that way, because there is no way to do it fast enough. Okay, I will look up the Tesla group. Actually, I do not recall having heard about them. But as you can see, you also say that they did it with a asynchronous rotating spark gap Tesla coil, which is way out of my experience league. I am mostly doing the solid state Tesla coils. Yeah, okay, as an alternative, yeah, okay. Yeah, it will work, because sure, if you change the frequency on the primary circuit or the secondary circuit, that doesn't really matter. As long as you change one of them for them both to match, then it will work. Now another really good source of GDT information is also found on Richie Burnett's website. Except again, this is not accessible from the website itself. You will have to find it either from searching or from a direct link, because he has a temporary folder on his website, and it's called GDT. And in this he has some winding techniques, again as you saw on the DataStreams website, and some practical results. This is with different materials and wire types, and as you can see, this is an unfinished work that never got completed, so this is why it was never made public. But the real true gem here is the typical gate drive waveform demonstrations here, where he simply describes in a few sentences for each kind of waveform what is wrong with your driver, what is wrong with your load, and how should you try to fix this, and what is probably the most common problem. So this is an absolutely golden source when it comes to really debugging on your gate drive when you think you have troubles there. And that is also very common, that you have some trouble here, either from using a wrong gate drive transformer material, or too few turns, or drivers that are not fast and powerful enough to drive the large IGBT gates that you are trying to drive. Okay, Arpad asks, the resonant frequency of the primary/secondary should be measured with them in place or not? Yeah, you should assemble your coil as it would be standing when you have it running, because the proximity of the primary coil to the secondary coil will affect the resonant frequency of the secondary coil. So everything that is near the coils and the proximity metal objects and so on will all affect the resonant frequency of the secondary coil. The primary coil is not that sensitive, as it has a much lower impedance, and it's not that picky to the surroundings, because you can say that the primary circuit is something that we just dump a whole lot of energy into, and we kind of forces it to behave the way we want. But the secondary coil is much more sensitive to surroundings. So clearly you should have it all assembled, and as a point where you can say as close to running setup as possible. Okay, let's return to the to my own DRSSTC design guide, and let's see if there are a few chapters that we did not cover yet. Okay, I did not talk much about rectifiers or the primary circuit itself. Neither did I talk about snubber capacitors or top loads. Now rectifiers, it's not you should read the chapter. You should understand the concepts of how to rate them and how to run them in parallel and so on. But there is no real magic going on here. It's simply a matter about dimensioning your components right here, and or again ensure even current paths. That is again overall number one design criteria here. In the bus bar and the primary circuit chapter, it's much about the inductances, whereas, yeah, as I mentioned so many times today, even current paths, as low inductance as possible, because when we force 2000 ampere through a certain amount of inductance, we will have a voltage spike develop over this inductance. And excuse me for a moment. And depending on how large this inductance is, we will see larger or smaller voltage spikes or transients. Now, our inductance all depend on the kind of topology that we use. Here you can see that the different amount of or the 4 different layouts on DC bus bar or your primary circuit is very much depending on your inductance in your circuit. The absolute best is the lowest, number 4, which is the laminated parallel plates, because this will nullify the inductance when it's very close together. So that is the most recommended. It's also one of the most hard to do, as it's much easier to do, as I have done myself, just do point-to-point bus bar connections. But if you do that, then at least use large copper bars so you can ensure as low resistance as possible. Now, primary coils, there is really no alternative to copper tubing. It is superior in so many ways, both in price, how easy it is to work with, and the electrical conductivity. Now, copper tubing made for water installations in houses is not pure copper, but even with its high copper content, it is still very fine for a multiplied 1000 ampere switching circuit. There is very little advantage to gain in using the 1-inch pipe compared to the I think it's called. It's 3/8 quarter inch pipe, as we have more copper, of course, for lower switching losses, but you would still have to water cool a larger tube when you're switching many amps compared to the smaller tubing. So there is really no advantage gained by using the larger tube. So this comes down to water cooling is just becoming a must, or you have to do that when you get over maybe 1000, maybe 1500, 2000 amperes in your primary circuit. And important here is, of course, to water cool it from the inside and out, and this has to do with the proximity effect, or the induction heating effect that happens, that the outer turns of your primary coil will heat the next turn, and these 2 turns will heat the 3rd turn. So the innermost turn of your primary coil would get heated by all the existing turns on your primary coil. So you will have the highest temperature rise on the inner circles of your primary coil. Here's a few tips on how to build your supports, and some more about skin depth. And this is another important point in why copper tubing is superior to solid wires, and it has simply to do with you can water cool it, which is very important, but also that the effective used copper area gets smaller and smaller with the higher frequency. So here's a small table of how deep in the material that we will be able to conduct. I think this was for 63% of the current is conducted in the, for example, at 200 kilohertz at 0.16 millimeter of the material. So if you have a 1 millimeter thick walled copper tube, we are not even utilizing 1/3 of the copper in it to conduct all the current. So solid wires has no place to go in high frequency coils, because there's no way we can utilize the copper. So it's wasted money, and it also do not give us the possibility of actually cooling a part that gets heated up very quickly. And Paulux asks about the websites, and yes, I will put all these websites into the description of the stream video when it's over. Yeah, Ilya, you can watch the stream later. It will appear as a video on my channel, so you don't need a sauna-proof phone if you are going to the sauna. But as I know you're Finnish, you will of course choose the sauna over me. So, cheers. So a good example of the induction heating effect on a primary coil can be seen here. This coil was not water cooled, and as we can see that the heat damages is just more and more extreme the closer to the middle that you get. So this is why you should water cool your primary coil from the inside and out. Okay, so let's get back to, let's see, snubber capacitors. Now snubber capacitors are a quite crucial point of your inverter, because this is what protects your IGBTs against the switching spikes, which are developed over the stray inductances in your DC bus bar layout. But also if your coil is hit at the secondary or the primary coil with a strike from one of your sparks. These are very heavy MKP capacitors, also known as GTO, from gate turn-off capacitors. They are known by this as they are originally developed for large SCRs, or what was the other type? Thyristors, because when they turn off in hard switching modes, the switching spike, which you will also see in IGBT inverters, the current spike here induced in the inductance would give a high voltage transient. And in order to capture this and dissipate it, we use a snubber capacitor or a snubber circuit. Now, most of the time you do not need more than just a simple capacitive snubber in your inverter. So there's really no need for for example, RCD snubber or just a RC or something like that. I give a few very basic guidelines on how to choose your snubber capacitance. These are all based on IGBT manufacturers' recommendations. And as you can do as in all my articles in the guide, you can go to the references at the bottom, and I will have a list of all the documentation or white papers and design guides and so on from different part manufacturers that I have used to write the guide from. Now the last part I think that we're getting to is the top load. Now the top load is really not a crucial component as per se. It's very important that it's round and smooth, because these things will help us control the electromagnetic field around the secondary coil, and this has some very important properties. This is why you don't see spheres used in dual resonant Tesla coils, because they do not provide the proper field shaping in order to protect the secondary coil and the primary circuit. Now, the toroid gives a great diameter, so you get your sparks from your breakout point even further away from your primary circuit. That is a very important point. But the whole field shaping around, when you have so many electrons building up on the surface of your toroid, this electrical field will prevent corona discharges on the top of your secondary coil. It will also prevent racing sparks on your secondary coil. It will, in a way, push your sparks away from itself, as you can say the same polarity that you have on your top load is what your sparks are coming from. So it will not try to seek back to itself. So this is also why it helps pushing sparks away from your coil. So for a dual resonance solid state Tesla coil, you should always use a toroid top load. You can even use a smaller one and then a bigger one on top of it, in order to do even further field shaping around the top of the secondary coil. But I have not found that it was necessary to do so. When you come to the whole discussion about what is needed when we talk about the solid toroid versus the skeleton toroid, I made 2 different simulations in IGBT to look at the resonant frequency and the capacitances and so on. So if we look at the effective shunt capacitance CES, which is 60 picofarads here, and we take a look at the skeleton, which is made up from 7 individual rings of a thinner pipe, we can see that the same effective shunt capacitance is now 57 picofarad. So we are down to maybe 5% difference. And honestly, in Tesla coil engineering world, plus minus 3 dB, which is 50%, is the same. It's roughly the same, because we don't know what is going on once we have huge sparks flying around anyway. So this is equally to each other, no doubt about it. Now, when it comes to material on toroids, there is aluminium is the superior choice. It's lightweight, it's cheap, it's easy to work with, it's easy to bend into shape, and it has just as good electrical properties as copper. So you don't see that huge difference in a copper versus a aluminium toroid or top load. Even aluminum tape can be used with the exact same results. As long as you have a large surface, you would not have a problem with the maybe few amps of current that you draw through the toroid. So something like, as I have mentioned many times earlier, the thermal management, it is not really a problem on the toroid itself, but it can get a problem on your breakout point. If you're not very on how large amount of power you're pushing out, you could see melting breakout points, which, if you lose it or it falls off and you suddenly have sparks flying uncontrollably around your top load, or the amount of power needed for for Tesla coil to build up enough charge on a very smooth surface toroid can simply be a too high load on your inverter, and you can simply risk destroying your inverter if it has no breakout point, simply because it will have to push such a huge amount of power into the secondary circuit before it will break out. So you have a huge circulating current that will go back and forth, and it will simply run into a self-destructive mode. Or you will have huge sparks lashing out here and there that you have no control over. So that can quickly get a little scary. Now there's a big difference between these aluminium ducting materials that you can find. That there is the flexible. There's 2 kinds of flexible. There is the hard aluminum flexible, and then there is a aluminum foil or metallized foil tubing here, and this has the problem that it's made from a polyester material that melts at around 70 degrees. So any kind of heavy spark that forms from this will simply melt a hole in it. So do not use this. It is not a great material. Okay, Arpad asks what affects the length/thickness of the arcs. Higher arm time, thicker arcs, and higher primary current, longer arcs at matching resonant. Right. You can say that your arcs are, if you're running at 120 bangs per second, so you have 120 arcs per second, and you go up in that speed to say maybe 300, 500 arcs per second, it will also get brighter because the spark channel that is formed in the air will get reused more and more times. What is really the deciding factor here is actually your MMC capacitance, because this is the amount of energy that you dump into each spark. So low impedance coils will produce thicker and heavier sparks than higher impedance coils. You can simply not fix it by adding longer on time, because you do not control the spark channel over that long amount of time. So even if you conduct for, let's say, 400 microseconds, you will not get the same effect in those 400 microseconds where the arc channel can actually switch multiplied times due to your resonance frequency. Then you will see that just dumping a higher amount of energy from the MMC capacitor, where we're simply talking how many joules of energy per pulse is being put into the system. So lower impedance coils with high MMC capacitance will produce much brighter arcs. Or you could also say this will also, the bigger toroids that you have, if your toroid or top load is too small, you will not have the charts available to actually feed a good thick arc from it. So it also comes down to your top load capacitance. But again, as we talk about primary capacitance, secondary capacitance, we are again back to impedance matching. We are again back to the whole matching up your Q and so on for the system. So once again, we bite our own tail. We have to go back and look at some entwined numbers in order to get this to make any sense. I have tried to discuss a little bit about losses in top loads, but this is practically only theory. I don't think I have experienced any problems with heating up on the top load, simply because the surface area is too great for it to ever heat up. Then there's a bit on calculating capacitances of different top load shapes. In case you're wondering, the turned toroids, the very smooth toroids made from a single piece of aluminum plate, it's called metal spinning. It's a metal forming technique used very much in lamp productions and for all kinds of balls and so on. I can show it up here that the well-known IKEA stainless steel balls that some people have used as top loads. These are made in the same way that you simply press a piece of metal on a lathe up against a form, and you, by that, shape your sheet metal into the form. So let's move back to the start of the guide. Or maybe here the ending part of the FAQ that we started with. That where to find parts to build a Tesla coil. Now, IGBTs are expensive, MMC capacitors are expensive, Snubbers capacitors are expensive. Copper coil or copper can be expensive, but it's relatively mostly fairly priced. Secondary coil forms can be expensive. But eBay is your overall friend when it comes to IGBTs and capacitors. Other good sources are your local radio amateurs or ham markets, so look out for those events. There are a lot of trade shows for radio amateurs and so on, where you can find all these high voltage parts as they are used in radio transmitters and so on. So there's a lot of components that you can find in those hobbies. Other than that, if you're looking for acrylic, copper clad, copper wire and so on, I also really do recommend eBay. This is a great way of finding internationally best priced components. I have often seen that locally materials in Denmark cost 3-4 times more than I can find them to on eBay from, for example, Germany, England, actually the whole of Europe, as we have do not have any tax barriers, so that's also a good market to shop in. When it comes to secondary coil forms or tubes, home improvement depots or contractors, if you're going for the really large diameter pipes, that is really where you have to go, because most home improvement depots do not have tubes that are bigger than 160 to 200 millimeters in diameter. Okay, so station 240 asks me what is the highest voltage Tesla coil you've seen in person, and that is actually my own DRSSTC 3, which you can see here. The coil itself measures 3 meters from ground to a breakout point, and it can produce 4-meter sparks. And I will say it gets quite scary when you're standing next to this, as it is quite uncontrollable when there's a little wind. And we had a small situation where we had the coil running out in the outside a garage, and we were standing just outside the garage door and just staying under the roof. And there was a couple of streamers that went over our heads and hit the rain gutter on the garage. So that was some good 40 centimeters above our heads. And then that quickly got interesting, and we moved back another 1-2 meters. So that is scary enough, but also the whole sound level and how you can feel the ionized air around the spark and the spark channel, the way it vibrates in the air, it's very special to experience. And the whole sound level is I usually describe this as a helicopter standing by in with its turbines just going up in pitch when rolling off, because it is really that loud, and ear defenders is always a must. Okay, let's see. Netfusher says the Teslian guy is a friend. His nickname is Tesla Toros at MOSFET Killer Forum. The MOSFET Killer Forum is a German Tesla coil forum. So check that out if you are able to read German or use Google Translate. It's another great high voltage forum. Let's see. Ilya says, yeah, most of the basic electronic components are made in China. That's why it's usually pretty safe to buy semiconductor components from China eBay. With caps, one should take more caution, maybe. I would say that I have one comment on the eBay capacitors, and that is that almost any induction cooker or induction stove made in the world comes from China today. So they have really stepped up their game in induction heater capacitors and resonant capacitors. And I think it's called the Dawn Cap. Is one of the oldest brands that are worth looking into. But you will also notice that they are considerably more expensive than similarly rated Chinese capacitors. But certainly do not buy any resonant capacitors that you cannot find a datasheet on, because if you do not know the numbers, then don't trust what is written on the eBay auction or so. So, I think this brings me to the end of this stream. I can say that I showed you the NMC calculator, but I also have a few other calculators that I would like to show you, which comes in handy. There's a small capacitor energy calculator. This is really just for checking out your DC link capacitors, or if you're experimenting with capacitor banks and so on, and is interested in the energy stored. Now the helical coil calculator is for calculating secondary coils. I made it possible to add in some capacitance here, which is a example of a top load capacitance, so you can get a resonant frequency. Now this is a very simple calculation. It is nowhere near as precise as a JVTC, but here you also only have to plug in a few additional numbers to calculate this. So this is again just a quick online tool for checking out your ideas instead of playing around with the whole JVTC setup. The IGBT gate drive calculator. This is a good small tool to check out if your IGBT or your gate drive design is powerful enough, what kind of power supply you have to use. Maybe a small single 24 volt 1 amp regulator is not enough. So you can calculate all this here. It is not including the gate driver transformer design itself. This is only based on the power needed to drive the gate of at the frequency that you want. But it also has a small specific section at the bottom that is for dual resonant solid state Tesla coils. So we take account for the shorter on times and the bangs per second. The Snubber capacitor calculator is quite simple. It has a Snubber capacitance that is calculated due to recommendations from IGBT manufacturers, and then it has a high and low inductance estimate. So if you do not know the inductance of your primary circuit, you can always estimate it and then pick a capacitance from that. Now the spiral coil calculator is for calculating your primary coils. It's quite again quite simple. Also you can add an tank capacitance for a resonant circuit, just to get a quick idea of the resonant frequency of your coil. So, if there are any more questions, please write them in the chat, and I will try to answer them to my best knowledge. And that will also make me have the last sip of my beer. Okay, if you have any questions, please just write a quick note that you have one and is writing it. So else I will say thank you all for joining in today and spending a good small 2 hours along with me and listen a little bit about yeah, design, theory, and compromises. So if we have to sum this up, it all comes down to how much money are you going to spend, how long are you willing to let this live, are you willing to sacrifice a little silicon or see some MMC capacitors melt, and so on. So it is really all down to how far do we want to push things, but certainly what I want to recommend is experiment with things, push it to the limit, turn up the voltage, turn up the current limit, and so on until things explode, then turn down 20%, and then you have a pretty safe point. That's another way of designing. So I will say goodbye and see you another good time, and I hope I gave you a lot of knowledge and ideas on how to start building your own Tesla coil. So if you have any further questions, please sign up at highvoltageforum.net, and we are a lot of experienced coilers that will help you with your design and troubleshooting your Tesla coil and so on. So until next time, see ya.